Hello everyone, welcome to this session on exception handling in Java. Today we will take a deep into one of the most essential parts of software development, managing and handling exceptions properly. This session is designed specifically for beginners and intermediate level Java developers who are looking to strengthen their foundation in exception handling. We explore the purpose, usage, and best practices of exception handling in real world applications. By the end of the session, you will understand not only how to use try, catch, finally, throw, and throws, but also why each construct exists and when it should be used. Exception handling is often the dividing line between a reliable application and one that crashes unexpectedly. It's not just a technical necessity, it's design choice that speaks volumes about the quality of your code. In professional environments, a well handled exception can make the differences between a great user experience and an application failure. Before we deep into the specifics, let's take a look at what we are going to cover in today's session. This agenda gives you a roadmap of what to expect from today's session. Your session is structured in a progressive and practical manner, starting from the basic concepts and gradually moving toward advanced features and best practices in exception handling. We will begin with understanding what an exception is and why it occurs. It's important to understand the concept deeply before jumping into the syntax. From there, we will move into the different types of exceptions, specifically checked and unchecked exceptions, and their role in Java. Next, we will explore the exception hierarchy in Java. You will see how exceptions are structured under the throwable class and how exception and error different. This hierarchy is essentially when deciding which exceptions to catch and which to let propagate. Then we will explore the core constructs like the try catch block, final throw, and throws. Those are the backbone of Java exception handling mechanism. We will break down their syntax and usage and with simple examples. We will also look at how to define your own custom exceptions and where they are most useful in real world applications. Toward the end, we will cover best practices, what to do avoid, and how to write cleaner, more effective exception handling code. We will finish off with real world examples and wrap up with a conclusion that ties everything together. What is an exception? Let's begin your journey by answering a fundamental question. What is an exception in Java? An exception is an event that occurs during the execution of a program that disrupts the normal flow of instructions. It is an object that represents an error or unexpected event which occurs while the program is running. Unlike compile time errors, which prevent a program from compiling successfully, exceptions occur at runtime. For instance, dividing a number by 0, trying to access an element outside the bounds of an array, or attempting to open a file that does not exist. All of those actions can trigger exceptions. Java provides a powerful mechanism to handle such events without crashing the program. Instead of terminating Java, always developers to catch those exceptions, handle them gracefully, and provide meaningful messages to the user. This is particularly important for software reliability and user experience. Imagine an ATM machine crashing every time there's network issue. An execution is not necessarily a bug, it's a way to signal that something unexpected occurred. Your job as developers is to be ready for it and ensure your program can respond appropriately. Let's now see why handling exception is important. Why handle exception? Now that we know what an exception is, the next logical question is why should we handle exception? The primary reason we handle exception is to prevent your program from crashing unexpectedly. By handling exceptions, we ensure that your application continues to function even when something goes wrong. For example, if a file is missing or a network connection fails, your application should inform the user and keep running. not just crash with a stacked trace. Another important reason is providing meaningful error messages. Without exception handling, Java applications throw stacked traces that regularly users cannot understand. A well placed exception handler can catch the error, explain it in plain language to the user, and suggest a corrective action. Furthermore, exception handling allows you to maintain the flow of execution. Imagine you are running a series of operations, reading from a file, processing the data, and saving it to a database. If an error occurs at any stage and is not handled properly, the entire sequence may stop. With proper handling, you can recover from errors, retry operations, or continue with alternative logic. Finally, from a development and debugging standpoint, catching exceptions help in logging errors and diagnosing problems more easily. Developers can track down which part of the code failed and why, making maintenance much more manageable. Exception handling in Java is not just a code requirement, it is an essential part of writing professional, user friendly, and resilient software. Next, let's understand the difference between exceptions and errors in Java. It's essential to difference between two important terms, exceptions and errors. Though they both originated from the same parent class throwable, they represent very different kinds of problems in Java applications. Let's start with exceptions. Those are issues that can typically be anticipated and recovered from. For example, if your program attempts to read a file that does not exist, it throws a file not found exception. This is something you as a developer can anticipate and handle by promoting the user to select another file or by creating a default one. Exceptions are your opportunity to write code that reacts to problems gracefully without crashing the entire application. On the other hand, errors represent more serious and unrecoverable problems. For instance, out of memory error or stack overflow error occurs when the JVM runs out of system resources. Those are beyond the control of the application and generally cannot be handled safely. Errors are not meant to be managed like exceptions. They signal serious issues in the runtime environment itself, something the application typically should not and cannot fix. Exceptions are recoverable problems, invalid user input, missing files. Errors are unrecoverable conditions, example JVM crashing, Knowing these differences helps you design your application's exception handling strategies better. Focus your try catch blocks around exceptions and leave errors to be logged and reported, but don't try to catch or fix them directly. Exception hierarchy. Now let's take a look at the exception hierarchy in Java, which is fundamental to understanding how exceptions work and how they are organized in the Java programming language. At the very top of this hierarchy is the throwable class. It is the superclass of all errors and exceptions in Java. Every object that can be thrown as an exception derives from throwable. Throwable has two direct subclasses. First one exception, second one error. Let's talk about exception first. This class represents condition that a responsible application might want to catch. Under this class, we have two key subcategories. First one checked exception. Those are checked at compile time. Example include input exception, SQL exception, etc. The compiler forces you to either handle them using try catch block or declare them using the throws keyword. Second one unchecked exceptions. Those are checked at runtime and include classes like null pointer exception, arithmetic exception, and array index out of bounds exception. The compiler does not force you to catch them, but you still should if you expect they might occur. Now moving to error. This class signifies serious problems that a typical application should not try to handle. Those include out of memory error, stack overflow error, and virtual machine error. Understanding this hierarchy is key when you write exception handling code. You can catch an exception at any level. For example, you can write a catch block that catches exception, runtime exception, or a specific exception like file not found exception. Understanding the difference between checked and unchecked exception is crucial for every Java developer. This different affects how you structure your code and what kind of exception handling mechanism you must use. Let's start with checked exceptions. Those are exceptions that are checked at compile time. This means that the compiler forces you to handle them explicitly either by catching them with a try catch block in the method signature. Common checked exceptions include input exception, SQL exception, and class not found exception. For example, when you are reading from a file using file reader, the compiler will warn you that input exception might be thrown. If you don't handle it, your code won't to compile. Those are recoverable exception situations that you can often and manage. On the other hand, unchecked exceptions are not checked at compile time. Those occur during runtime and are typically caused by programming bugs such as logic errors or improper use of applications. Examples include null pointer exceptions, array index out of bounds exception, and arithmetic exception. Unchecked exceptions are subclasses of runtime exceptions. Java assumes that those are programmer errors, things you should fix in the code, not necessarily handle during execution. However, you can still catch and handle them using try catch blocks if you want to add more resilience to your code. Checked equals to compile time must handle, unchecked runtime optional to handle. Common secured exceptions. In this slide, we will look at some of the most commonly encountered checked exceptions in Java. As we just discussed, checked exceptions are the ones that the compiler forces use to handle. They are predictable and typically occur during interaction with external systems such as file systems, databases, or network resources. Let's go through a few examples in detail. First one, input exception. This is one of the most frequently encountered checked exceptions. It occurs when an input or output operation fails. For example, while reading from a file or writing to it, if the file is not found or the disk is full, an IO exception will be thrown. It belongs to the java.io package and often appear when working with file streams and network sockets. Second one, SQL exception. This exception is part of the java.sql package and is thrown when there is a database access error. Suppose you are executing a SQL query and there is a syntax error or a table does not exist. You will get a SQL exception. It's essentially to handle this properly because database failures are quite common in enterprise applications. Third one, class not found exception. This exception occurs when the application tries to load a class at runtime. For instance, using class dot for name and the class is not found in the class path. This is important when working with JDBC or reflection. All of those exceptions require you to either wrap your code in a try catch block or declare the method using the throws keyword. Handling them effectively helps create programs that are not only robust but also user friendly, as users can receive clear messages and fallback options when something goes wrong. Common unchecked exception. While checked exception help us anticipated problems with external resources, unchecked exceptions typically point to issues in your program's logic. Those exceptions extend the runtime exceptions class and are not checked at compile time. Those exceptions extend the runtime exceptions class and are not checked at compile time. This means the compiler will not force you to handle them, but it's still good practice to anticipate it. Let's explore a few common unchecked exceptions. First one, arithmetic exception. This is a throw-in when an illegal arithmetic operation occurs, such as dividing a number by zero. Although this seems trivial, if not handled, it can crash your program. For example, int result equals to 10 by 0. We'll throw an arithmetic exception. Second one, array index out of bounds exception. This occurs when you try to access an array element using an invalid index. For example, if your array has 3 elements and you try to access the fifth element, Java will throw this exception. It's very common mistake, especially in loops. Third one, null pointer exception. This is probably the most infamous Java exception. It happens when you try to use an object reference that has not been initialized. For example, calling a method or accessing a field on a null object. Null pointer exception can be avoided through proper checks, and with Java 8 plus the option says like sockets or threads. Those actions are critical and must occur whether or not an error was encountered. For example, here no matter what happens, whether the file is read successfully or an exception is thrown, the final block is ensures the file stream is closed. One key point, the final block executes even if you include a return statements in the try or catch. It does not execute only in rare scenarios like when the JVM crashes or if your call system.exist before the final block runs. This block is essential for preventing resources leaks and ensuring that your application remains stable and efficient. It's best practice to always include finally when dealing with resources. This risk. Unchecked exception can cause major issues in production systems is not careful managed. It's best practice to write a defensive code for instance checking for null before use validating inputs and using safe indexing. The try block. The try block is the starting point of Java structured exception handling system. It is where we write code that we believe might throw an exception. Instead of allowing your program to crash when something goes wrong, we encapsulate that risky code inside a try block to catch and handle potential problems. The syntax for a try block is straightforward. In this case, dividing by 0 will throw an arithmetic exception. If this line is outside a try block, it would crash the application. But inside the try, we can pair it with a catch block to handle the issue gracefully. The try block must be followed by at least one catch or final block. Otherwise, the compiler will throw an error. It can exist on its own. What's important to understand here in the mindset? You use try blocks when you are dealing with risky, be it file access, database connections, user input, or even complex calculations. By using a try, you are telling the JVM, I know something might go wrong here and I am ready for it. The size of your try block matters too. It should be as small as possible, only wrapping the lines of code that may cause an exception. The catch block. After wrapping risky code inside a try block, the next logical step is to handle any exceptions that occur, and that's where the catch block comes in. The catch block allows you to define how your program should respond when a specific exception is thrown. Here, exception type is the type of exception you want to catch. For example, IO exception, arithmetic exception, or even the base exception class if you want to catch anything. Let's look at an example. In this example, when the division by 0 happens, Java skips the rest of the try block and immediately enters the catch block. The error message is printed and the program continues running, no crash, no termination. Inside the catch block, you can log the error, display a user friendly message, retry the operation, or even rethrow the exception. It all depends on how critical the operation is. You can also catch more than one type of exception using multiple catch blocks, which we will explore in the next slide. One thing to remember, always catch the must specific exceptions first, then the general ones. Catching a generic exception before a specific one, like IO exception, will make the specific block unreachable, and that's compile time error. Multiple catch blocks. In many real world applications, a single try block may include operations that could throw multiple different exceptions. For example, when reading from a file, you might get a file not found exception, but while processing its contents, you might face an IO exception. Java allows you to handle this using multiple cache blocks, each tailored to a specific exception. Each catch block is checked in sequence. Java matches the exception thrown with the first compatible block, and once it finds a match, it executes that block and skips the rest. Important rules: always catch more specific exception before more general ones. For example, catching IO exception before file not found exception is incorrect because file not found exception is a subclass of IO exception. Catching the superclass first makes the subclass block unreachable, resulting in a compilation error. This feature gives you flexibility and better control over how different types of exceptions are handled. For example, you might want to log a file not found exception differently from a SQL exception or prompt the user differently. This practice also improves code readability and maintainability, making it clear what kinds of errors are expected. In Java 7 and above, you can even combine multiple exceptions into a single catch block. The final block in Java is very special construct. It is designed to execute always, regardless of whether an exception is thrown or not. Whether your try block completes successfully, throws an exception, or even if a return statement is executed, that final block will still run. The syntax is: so what's the purpose of the final block? Primarily, it is used for cleanup operations such as closing file streams, releasing database connections, or shutting down resources like sockets or threads. Those actions are critical and must occur whether or not an error was encountered. For example, here no the final block in Java is very special construct. It is designed to execute always, regardless of whether an exception is thrown or not. Whether your try block completes successfully, throws an exception, or even if a return statement is executed, that final block will still run. The syntax is: so what's the purpose of the final block? Primarily, it is used for cleanup operations such as closing file streams, releasing database connections, or shutting down resources like sockets or threads. Those actions are critical and must occur whether or not an error was encountered. For example, here no matter what happens, whether the file is read successfully or an exception is thrown, the final block is ensures the file stream is closed. One key point: the final block executes even if you include a return statements in the try or catch. It does not execute only in rare scenarios like when the JVM crashes or if your call system dot exists before the final block runs. This block is essential for preventing resources leaks and ensuring that your application remains stable and efficient. It's best practice to always include finally when dealing with resources. The throw keyword. Now that we have explored how Java allows us to handle exceptions using try, catch, and final, let's shift your focus to how we can manually trigger exceptions when something unexpected happens. This is done using throw keyword. The throw keyword allows you to create and throw your own exceptions during program execution. This is useful when you want to enforce specific rules or validate data and you decide that an exception should occur if a condition is not met. A few important notes about the throw keyword. We can only throw an exception at a time. The object thrown must be a type of throwable. The object thrown must be of type throwable. You usually throw either built-in exceptions like illegal argument exceptions or custom exceptions, which we will discuss later. The throw keyword gives you full control over the flow of your application, especially when you want to stop execution due to a validation failure or illegal operation. The throws keyword. While throw is used to actually throw an exception, the throws keyword is used to declare that a method might throw one or more exceptions. It tells the Java compiler and any method callers, hey, this method might encounter an exception, be prepared to handle it. Here the basic syntax. In this method, we are telling Java that the read file method might throw an IO exception. If someone calls this method, they are responsible for handling that exception, either a try catch block or by propagating it further up the chain using their own throws declaration. You can also declare multiple exceptions using throws. The throws keyword is essentially for exception propagation, which we will explore later, but keep it in mind. You can only declare checked exceptions using throws. For unchecked exceptions, you don't need to declare them. So you can if you want to document them explicitly. Throws helps you to design applications by being transparent about which exceptions might occur, making the code safer and easier to maintain. Custom exceptions. Java provides a rich set of built-in exceptions, but sometimes your application may need to throw errors that are specific to your business logic, things that built-in exceptions cannot fully represent. That's where custom exceptions come into play. A custom exception is a user-defined class that extends the exception class or one of its subclasses. By creating your own exceptions, you can provide clear, context specific errors, messages, and enforce your application's rules more meaningfully. Let's look at a quick example. This is a very simple custom exception that checks for a business rule. Say, user must be over 18 to register. Why this is useful? Your exception names describe the problem, make the code easier to read and maintain. It keeps error handling logic separated from business logic. You can enrich your exception within additional data or methods if needed. For example, include error codes or user IDs. Here are a few tips for custom exceptions. Always extend exception for checked exceptions. You can also extend runtime exception if you want to make it unchecked. Include useful constructors to allow flexibility. Custom exceptions help you build clear, modular, and more meaningful error handling systems that align closely with your application's domain. Create a custom exception. Let's now walk through the steps involved in actually creating and using custom exception in Java. Custom exceptions are especially useful when the built-in Java exceptions are too generic to describe the specific issue in your application. Here are three main steps to create a custom exception. First one, define the exception class. Create a class that extends the exception class. If you want to be unchecked, extend runtime exception instead. This class has a constructor that passes the error messages to its superclass exception, which stores and returns it when needed. Second one, use the exception in logic. Let's say you are building a banking application and want to ensure that withdrawal amounts are not negative or zero. Third one, handle it in calling code. When calling a method that declares a custom exception using throws, you need to handle it with a try catch block. This makes your error handling much more descriptive and your application's logic. Catching a generic illegal argument exception, for example, clearly communicate what went wrong. Custom exceptions are not just about throwing errors, they are about building readable, maintainable, and domain driven applications. Try catch finally example. Now that we have covered the individual components, try catch finally and even custom exceptions, let's see how those parts come together in a real world Java example. This will help us understand the practical flow of exception handling. Here simple example that attempts to open a file, read its contents and handle any issues that any arise. Let's break this down. The try block is used for the core logic, reading a file line by line. Two catch blocks are used, one for file not found exception and another for IO exception. This ensures different types of issues are handled appropriately. The final block ensures that the file is always closed. Nested try catch. There are situations where you might need to handle exceptions inside another try block, and that's where nested try catch blocks come into play. A nested try catch means placing one try block inside another. This technique is helpful for managing exceptions at multiple levels of execution, especially in complex applications. In this code, the inner try catch handles the invalid array index. The outer try catch handles the division by zero. This structure allows for more control over different exceptions types at different stages of the logic. For instance, you might want to handle a file reading error differently than a data processing error. Nesting allows you to isolate the logic and error handling cleanly. Deep nesting can reduce code readability. Try to refactor your code into methods and use exceptions propagation where needed. Multicatch features. In Java 7, a very useful feature was introduced to simplify exception handling. The multicatch block. This allows us to catch multiple types of exceptions using a single catch block. It helps eliminate redundant code and improves readability when handling logic for different exceptions is the same. The syntax uses a pipe symbol to separate exception types. The variable e in this example is implicitly final, which means you cannot assign a new exception object to it inside the catch block. That's to ensure type safety and predictability. This feature is especially useful when you are calling multiple methods that may throw different exceptions. The exception handling logic is the same or very similar. You want to reduce code clutter and duplication. One important rule: all exception types listed in a multi-cache must be unrelated in the inheritance hierarchy. You cannot cache both exception and IO exception together, as one is a subclass of the other. This would result in a compile time error. Multi-cache blocks are a modern and clean way to handle multiple exceptions without writing a repetitive code, making your applications both readable. Exception propagation. Let's now talk about a powerful and often misunderstood concept in Java: exception propagation. When an exception occurs and is not handled in the method where it happened, it gets propagated up the callback stack to the method that called it, and so on until it's either handled or the program terminates. Here, simple example. In this case, method B throws an IO exception but does not catch it. The exception is propagated to method A, which must now handle or declare the exception using throws. If method A also does not handle it, the exception continues to propagate reaching the main method. If it's still not handled, the JVM handles it by printing a stack trace and terminating the program. Here, what you need to know about exception propagation: it happens automatically if an exception is not caught. Only checked exceptions need to be declared. You can use the throw clause to pass the responsibility to the caller method. Exception propagation is very useful in layered application. For example, in a multi-tier architecture, you may want to throw exceptions from the DAO to the service and then handle them in the controller to show meaningful error messages to the user. However, don't overuse propagation. If a method can handle an exception meaningfully, should do so, otherwise propagate it with clear documentation. This slide is all about clearing the confusion between throw and throws, two keywords in Java that are commonly mixed up by beginners. Even though key sound similar and are related to exception handling, they serve entirely different purposes. Let's begin with throw. Throw is used inside a method to explicitly throw an exception. It is followed by an instance of the throwable class, either a built-in or custom exception. Example. In this example, the program will immediately terminate the method and transfer controller to the nearest catch block. Now let's look at throws. Throws is used in the method signature to declare that a method may throw one or more exceptions. Its way to end the method's caller to be prepared to handle or propagate those exceptions. Key differences. Features throws. Purpose actually throws an exception declares potentially exceptions. Usage location inside a method in method declaration. Followed by object of exceptions. Exception class names. Use throw to trigger an exception. Use throws to signal that an exception may be thrown. Real time example. Let's now bring everything we have learned together in a real world scenario. This example will help you see how exception handling is used in practice, especially when dealing with resources like files or database. Suppose you are building a simple text editor or file viewer. One common operation is reading a file from that system. However, this task is loaded with risks. What if the file does not exist? What if there permission issue? What if the content format is invalid? What happening here? File not found exception is caught if the file does not exist. IO exception handles other input output problems. The final blocks ensures that reader is closed to prevent memory or resources leaks. This kind of code is critical in production environments where you cannot afford to crash the app just because of missing file. Users get a helpful message and the program continues running. This real-time use case reflects robust program. You anticipate problems and you handle them cleanly, which is in the hallmark of good software engineering. Best practices. Writing exception handling code is not just about catching errors, it's about catching them the right way. Let's go through some important best practices to ensure your Java applications remain robust, maintainable, and professional. First one, catch specific exceptions, not general ones. Avoid catching generic exceptions like exception or throwable unless absolutely necessary. Catch the most specific type you expect, for example, input output exception instead of exceptions. Improves clarity and prevents you from unintentionally catching unrelated exceptions. Second one, don't use empty catch blocks. An empty catch blocks silence the errors, making debugging extremely difficult. Always log the exception or show a meaningful message. Third one, always use final or try with resources. Use the final block to close resources like files, sockets, or database connections. Alternatively, use try with resources, which automatically handles cleanup. Fourth one, don't use exceptions for flow control. Avoid using exceptions to control logic. For example, don't throw an exception to break out of a loop. Exceptions should be reserved for exceptional conditional, not normal program flow. Fifth one, document exceptions. Always document the exceptions a method can throw using JavaDoc and the throws clause. This helps other developers understand the risks and handle them properly. Sixth one, use custom exceptions wisely. Create custom exceptions when they add clarity. Don't overdo it. Use them only in a meaningful abstraction. Conclusion. We have now reached the final slide of this session, and I want to take a moment to recap what we have learned and emphasize why exception handling is such a skill for every Java developer. Exceptions are unexpected events that occur during program execution. Unlike errors, they can and should be handled. Java offers a robust set of tools, try, catch, final, throw, and throws, to help manage those events gracefully. We difference between checked and unchecked exceptions, learning that checked ones must be handled or declared, while unchecked ones signal programming errors. You now know how to use multi-catch blocks, nested try-catch, and how to propagate exceptions up the call stack using throws. We create custom exceptions to reflect specific business logic, giving your application more clarity and maintainability. We reviewed a real world file handling example to understand how those tools come together in practice. And finally, we discussed best practices because writing clean, understandable, and maintainable code is just as important as writing code that works. Thank you for joining this session on exception handling in Java.